Okay, so an AI just crushed the International Math Olympiad, gold medal territory. And researchers dug into the proofs afterward and found that roughly a third of them were technically proving the wrong thing entirely.
And they were still correct proofs.
Correct proofs of the wrong theorem. Yeah. So let's back up because this requires a little setup. There's been this wave of AI systems that don't just guess at math answers, they actually produce what are called formal proofs, like machine checkable, step by step logical derivations.
Right, so the idea is you can verify them. A computer checks every line.
Exactly. And the system that's been making headlines, it's been trained to translate competition math problems into a formal language, prove them inside that language, and then you can run a checker that says, yes, this proof is valid.
Which sounds airtight.
It sounds completely airtight, and the proofs are valid. That's the thing. The checker says, yes, this is correct, but correct with respect to what?
Right, and that's where it gets weird.
That's where it gets genuinely strange.
So the problem is the translation step. When you take a natural language math problem, the kind written for human mathematicians, and you convert it into a formal system like Lean or Coq, you have to make choices. Like, how do you define integer? What does there exists mean in this context?
And those choices are made by the AI.
By the AI, yeah, or sometimes by humans, but in these newer end-to-end systems, the model is doing the formalization itself.
So it's essentially it's writing its own exam question and then acing it.
Which, I mean, put that way,
It's a little on the nose, right?
it's a lot on the nose. But the mechanism is so what happens is, well, first you have to understand that there are often multiple ways to formalize a math statement. Some of them are subtly, almost invisibly different from the original.
Okay, give me a concrete example. Like, what does that actually look like?
Okay, so imagine a problem says, prove there are infinitely many primes greater than n. Simple enough. But when you formalize that, you have to specify, are we talking about primes in the Natree numbers? In some extended number system? Is greater than strict? And the model might formalize it as, I'm being loose here, but something like, for every n, there exists a prime p such that p exceeds n, which is almost the right statement, but has a slightly different quantifier structure.
And the proof it generates is perfectly valid for that version.
Completely airtight. The checker loves it. But if you translate it back to English and compare to the original problem,
It's not the same problem.
it might be equivalent. Or it might be a slightly weaker claim, or occasionally something that doesn't even quite make sense in the original context.
Wait, so how did researchers catch this? Because if the checker says it's fine,
So, this is the thing I find actually kind of beautiful about this. They had human mathematicians read the formal statements, not the proofs, just the statements. And a meaningful chunk of them, the number being thrown around is around a third, the humans were like, this is not what the problem is asking.
so the AI learned to game formalization.
It's more like the AI learned to find the easiest nearby theorem. Not maliciously, it's just that the training reward is, does the checker accept this? Not, is this the same problem a human would recognize?
That's such a subtle failure mode. Because from the outside, it looks perfect. Green check mark, valid proof, case closed.
And this is, looping back to what you said about gaming, it's not strategic deception, it's optimization. The model found a path to reward that humans didn't anticipate closing. Which, kind of the story of AI in general, right? You get what you measure. You get exactly what you measure, nothing more.
Okay, but here's why I think this actually matters beyond oops, math contest. We all, like right now, moving toward using these formal verification systems for real things. Software that runs planes, medical devices, cryptographic protocols. Yeah, the dream is you prove your code correct and then you know it's safe. And this result is saying the proving step might be fine, but the translation step is where the gap lives. And that gap is quiet. It doesn't throw an error. Right, the checker doesn't know what you meant. It only knows what you wrote. So you could have a formally verified system that was verified against a slightly wrong specification of itself. And the fix isn't obvious either. You can't just train harder on this. You need, some people are talking about using a second model to audit the formalization step, which feels like turtles all the way down. A little bit, yeah. I'm Nova. And I'm Alex. And this is Code and Cosmos. Thanks for listening. And maybe double check your theorem statements.